Okay, this video is called Why Starch Prevents Cancer. We're going to talk a little bit about insulin resistance here, and you could also call this talk Why Elevated Insulin Levels Increase Cancer Risk. And part of the point of this whole talk is high-fat diets are connected to increased risk of diabetes, and they're connected to increased risk of hypertension, and they're connected to increased risk of cancer. And I've gone through other talks where I talk about how high-fat diets increase the risk of cancer in multiple ways. But I'm going to go through the issue of how they do it by increasing insulin resistance in this talk. Okay, so first of all, we're going to start out with what does normal insulin function do? When the blood glucose is elevated, insulin is released by the pancreas. It comes to the cells like the skeletal muscle cell plasma membrane, has an insulin receptor. It binds to the insulin receptor. That sends a message that the glucose type 4 transporters, which are stored in vesicles in the cytoplasm, should travel up to the plasma membrane. They merge with the plasma membrane, and then they form a channel to allow glucose to come into the cell. Okay, glucose comes into the cell, it gets phosphorylated, it can run through glycolysis, for example. This is normal insulin function. Okay, when this works well, that's called good insulin sensitivity. When the insulin's not working well, it's not able to get these glucose transporters up to the plasma membrane, that is called insulin resistance. And normally, a very large amount of the postprandial, prandial means eating, postprandial blood glucose goes into the skeletal muscle. It's a good spot for it because it can be stored as glycogen. The skeletal muscles is your biggest organ system in your body, and it can store a lot of glycogen, and up to 70% of your postprandial glucose can, go into your skeletal muscle, a lot of it, okay? All right, now this guy, Michael Brownlee, he wrote the greatest paper ever written about diabetes. It's so beautiful. We've talked about it before. It's like the Sistine Chapel of diabetes papers, of all scientific papers. This guy's beyond a genius. He had diabetes type 1, and he wanted to save his own life, and the guy's a genius, and he devoted his whole life to researching diabetes. Here's an illustration from his paper. It's a great pathobiology of diabetic complications, a unifying mechanism. This paper came from, he won the Banting Award, Best Diabetes Researcher in the World in 2004. So anyways, what he talked about is when the gradient in the intermembranous space here of the mitochondria gets too high, the direction of electron transport of the intermitochondrial membrane will reverse, and you'll start dropping more electrons from the transport chain, which is like a fireman bucket brigade handing off electrons. It'll drop them down into the mitochondrial matrix, and you'll bounce off of oxygen and create superoxides, okay? So I'm going to go into more detail about what all this means, but what I'm getting at, the whole point of this talk for today is what is the relationship between insulin and cancer. It's all going to make sense in a moment. I've got to give you the backstory. Okay, so excess dietary fat, especially saturated fat, causes insulin resistance around this level between coenzyme Q and and complex 3 for protein pumping protons. Okay, here's the inner mitochondrial membrane, IMM. Here's the outer mitochondrial membrane, usually abbreviated OMM. And this is the intramembranous space in between these two membranes where the protons are usually pumped to build up a gradient, kind of like an air pressure gradient. Then you harvest the gradient over here at complex 5, allowing a protein to re-enter the matrix. And the energy of that is used to couple a phosphate to ADP. AD is adenosine diphosphate, as in 2 phosphates, and this added phosphate makes it adenosine triphosphate, having 3 phosphates, okay? And that's how you make energy for a cell. That's how about 90% of the energy in the human body is made. This is the key to life on Earth right here, this intermitochondrial membrane, okay? And excess dietary fat inhibits that. Excess dietary fat is a bad thing. Okay, then why does the fat do this? The fat's able to get into the skeletal muscle faster than the glucose can. The fat is able to intercalate into the outer leaflet of the plasma membrane of the skeletal muscle cell. It's something that's been called the flip-flop maneuver. Okay, it can be protonated, make itself nonpolar, get into the outer leaflet, flip into the inner leaflet, then move into the cytoplasm of the skeletal muscle. The best paper on this subject is by Anthony J., not the Anthony J. we know for estrogens, but a different Anthony J., James Hamilton, Putative Inhibitors of Fatty Acid Transport Across Membranes by CD36. Okay, so the point was they inhibited all these so-called fatty acid transporters, and it didn't matter. It was just coming across the plasma membrane on its own. And so this is another reason why you can't win with a high-fat diet. All right, so then it can get into the mitochondria and cause insulin resistance, okay? All right, so here's an example of insulin resistance. When you get excessive amounts of fat into the mitochondria too quickly, they'll overwhelm the mitochondria with electron transport, especially SAT fat. SAT fat produces more NADH more rapidly because a PUFA has double bonds, and that leads to decreased NAH going to the inner mitochondrial membrane. It doesn't happen as quickly. So anyways, the mitochondria senses this as so-called overnutrition, and it says we can't handle any more nutrients coming in here, no more glucose coming in here, for example. And then this will block these glucose type 4 transporters from going up to the plasma membrane. So that's why it's called insulin resistance, because insulin will bind to the plasma membrane of the skeletal muscle, but it won't be able to get the glucose type 4 transporters to go up and merge with the plasma membrane to allow glucose in. So the glucose can't get into the cell. It bounces off, okay? And it stays high in the blood, and that gives you high blood glucose, hyperglycemia. So this is what happens in insulin resistance, okay? You need to know this. This is a fundamental thing to understanding disease. Okay, so we talked about how excess dietary fat will do that. Also, omega-6 cooking oils, they will lead to the production of toxic aldehydes like hydroxynonenal, and that's an inhibitor of complex 5, the ATP synthase. Okay, so that also leads to similar problems. This is a little bit more detail about when you start reversing electron transport, you drop more and more electrons down onto oxygen in the mitochondrial matrix. You produce more and more superoxides. The mitochondrial matrix has a way to handle them. It has superoxide dismutase, which converts it into hydrogen peroxide, and then there's additional enzymes like catalase, glutathione peroxidase, convert it into harmless water. Okay, but if there's free iron in the mitochondrial matrix, you can run the Fenton reaction, Fe for iron, ferrous, and Fe for Fenton reaction, and start producing hydroxyl radicals and do a lot of damage. So we're not going to go into all this, but what I'm trying to make the point is insulin resistance is starting off a cascade of harmful reactions like all of this stuff down here. Okay, so now a key point is to get the idea of glucose tolerance and its relationship to dietary fat. If you just eat a starch, you get a little bump in blood glucose. That's normal. You're supposed to get that. But then you stay in the normal zone with blood glucose a prolonged amount of time. You feel good. Your hunger's satisfied. You got good energy. On the other hand, if you eat dietary fat first, it gets into the skeletal muscles, causes insulin resistance like we just showed, so-called overnutrition, and then the blood glucose can't get into the skeletal muscles, and you have a prolonged high blood glucose level, hyperglycemia. And that occurs after you ate, so that's postprandial. That means after eating, hyperglycemia. Okay, and you'll be accumulating fat in your skeletal muscle. That's the first detectable finding of insulin resistance, is accumulation of fat in skeletal muscle. That's been shown with nuclear magnetic resonance spectroscopy, and Roy Taylor and Gerald Shulman were two of the big workers on that. They both deserve Nobel Prize, those two. Okay, now I'm going to show you a little bit more about blood glucose curves, and this is actually pretty useful. I know it's a little complex, but it'll make sense in a moment. So between these two green lines, here's the upper level, normal, lower level, and normal. These are healthy blood glucose levels. Just say you want your blood glucose to be in this spot between the two green lines most of the time. All right, and this is the blood glucose kind of gradually coming down from the last meal. Now, if you eat just simple sugars and also sweets, foods with a lot of sugar added, and even some really, really sweet fruits, I get rebound hypoglycemia from bananas. Okay, your blood glucose kind of spikes rapidly, and then it'll come down kind of rapidly. The pancreas has a tendency to overcompensate, release too much insulin too fast, and you'll get rebound hypoglycemia. Okay, I realize some people do not get rebound hypoglycemia from eating really sweet bananas, but I do. All right, anyways, you don't really want that because you'll often grab for more sugar and just repeat this thing, and you'll have a roller coaster blood glucose curve. All right, so now here's what happens if you eat dietary fat followed by carbohydrates. You get what I just showed in that last picture. The dietary fat causes insulin resistance, and then the carbohydrate blood glucose can't get into the cell, and you end up with this prolonged elevation of blood glucose, prolonged postprandial hyperglycemia. Now, if you eat a starch that's low in fiber, something like white rice, you get a little bit of a spike, not that much, and it stays a little high, gets down in this zone. It's actually a decent food. The curve's a little bit better than what I drew it here. Fruit that's not as sweet can put you in this range as well. All right, so anyways, though, what I want to show you is the best food is your high fiber starches, and you'll keep a more prolonged blood glucose in the healthy, optimal range where you want it. And you satisfy your hunger with the fewest number of calories. So you're skinny, and you get less of a bump in your insulin. This leads to insulin resistance. When you eat the fats first, and you're going to have the pancreas keeps on pushing out more insulin, trying to get this carbohydrate to be pushed in, forced into the skeletal muscle. So this causes hyperinsulinemia. I should have written that on the curve, as well as hyperglycemia, postprandial hyperglycemia with hyperinsulinemia, high insulin levels. You don't want those high insulin levels. And let me show you one of the big reasons as it relates to cancer. So the whole talk was building up to the point I'm going to make here. One of the things that insulin does is it binds the skeletal muscle cell, and then it can get the glucose, some glucose to come in through the glucose type 4 transporters, depending on how much insulin resistance there is. But one of the things that it does is it also causes hydrogen protons to be pumped out into the extracellular space. And glucose is also mitogenic, meaning that it promotes cell growth and replication. Mitogenic is related to the word mitosis, for cell division. But what I'm trying to tell you is this is kind of the pattern one sees. Now, it's normal for a little bit of this to happen all the time. But what I am telling you is when you have high levels of insulin, as associated with more pumping of acid, protons, H+, into the extracellular space. It's called extracellular acidification. Okay, and this pattern of extracellular acidification is associated with favoring a cancer milieu, which is acidotic, okay? And the insulin is mitogenic. So this is one of the ways that excessive dietary fat promotes cancer, and why you don't want chronic high insulin levels with prolonged hyperglycemia, because you're getting more and more insulin, and not all the insulin effects are blocked. The glucose type 4 effects are partially blocked. We talked about that with insulin resistance, but you can get chronic elevation of pumping acid into the extracellular space, which suppresses your immune system. You'll also get an elevation. I'm not going to go into all the detail now. This is just an introductory talk. You're also going to get elevated to your sympathetic autonomic nervous system, SANS, which is stress, and those hormones, cortisol and catecholamines, are going to decrease immune system function. So your immune system function is triple screwed in this case. Number one, because of high insulin levels. Okay, pumping out more protons, acidification in the extracellular space, that weakens the immune system. Number two, fat intrinsically suppresses the immune system. Number three, the high insulin levels activate the sympathetic autonomic nervous system, releasing more cortisol and catecholamines. That also suppresses the immune system. All of these things weaken the ability of the body to fight cancer. Okay, so I just wanted to show this. I thought this was especially interesting, the idea that elevated insulin levels lead to elevated secretion of protons into the extracellular space, extracellular acidification. And this is classic for cancer, okay? So all of these occur to some extent under normal conditions. That's all well and good. But what I'm saying is chronic high insulin levels due to high-fat diets increase extracellular acidification, suppressing the immune system and favoring a cancer microenvironment, tumor microenvironment, cancer milieu. And so I thought that was interesting. That was the point of this talk. I hope you found that interesting.